All right, I'm going to go ahead and get started. Thank you all for joining us here today for the UG2 webinar. This is the 22nd webinar in our series. I can't believe it's already been that many. And this is the second webinar in our Early Career Spotlight series, so that's really exciting as well. And if you haven't noticed, I am not Georgia Coward, our UG2 coordinator. I am just filling in. She is on maternity leave, so big congrats to Georgia, and we're expecting her back late November, sometime in December. So as always, just a shout out to our amazing steering committee and sponsors who make everything happen behind the scenes, from our sub-focus groups to planning of our workshops. And then here's just a brief agenda for the day. I just have a couple quick updates to do, and then I'm going to hand it over to Joe Gradone, our early career sub-focus group lead, and he will introduce our speakers. So just some upcoming events that we have. So as a reminder, our UG2 2026 workshop is going to be May 18th to 20th. And this is going to be at the University of South Florida. And this will be in St. Pete, Florida. Registration for this is going to open in January, so keep an eye out for that. And planning is kind of already underway, but it's really going to kick off, I'd say, in December. So things are moving. We're now accepting ideas and moderators for breakout sessions. So if you guys have any thoughts, feel free to send them to info@underwatergliders.org or send them straight to Georgia. And then at the Ocean Sciences meeting in February of 2026 in Scotland, we're going to have a town hall. This is titled Underwater Gliders in Action, Ocean Emergency Preparedness. And this is in collaboration with the EGO group in Europe. And then you should have received our UG2 newsletter in July. If you haven't received it and would like to be on that list, you can sign up on our website, and our next edition is scheduled to come out in December. So keep an eye out for that as well. And with that, I'm going to pass it on to Joe.
Thanks, Cassie. So yeah, I'm Joe Gradone. I'm gonna be doing the Vanna Whiting between our awesome speakers today. So I will do an introduction, and then I'm not gonna bother reading your titles because you're gonna tell us more about your work than I will in just your title. So first up is Josh Soll. So Josh is currently a master's student at the University of the Virgin Islands. His thesis research is related to whale acoustics using Slocum gliders and automated whale detection algorithms. He's an advanced open water scuba diver, environmental advocate, artist, photographer, and overall outdoor enthusiast. And he is also fluent in Spanish and enjoys every opportunity to speak with others. So I will pass it over to Josh. You can just share your screen and take it away.
Thanks, Joe. All right, I'm going to share. Let's see, you should be able to see my screen. Okay. Well, good afternoon, everybody. Again, my name is Joshua Soll, and I'm a master's student at the University of the Virgin Islands. The school is a kind of smaller school located on St. Thomas, an island territory in the United States, kind of in the Eastern Caribbean. And my thesis, which I will soon be defending, is titled The Automated Detection and Classification of Baleen Whales in the United States Virgin Islands and Puerto Rico. So quick roadmap. I'm just going to kind of loosely discuss some different parts of my project, including a little bit of a background. I'll cover some methods of my work, some of the findings, and then some of the broader impact that I hope this research will have. And then I'll leave time for questions. And I also have a few short clips of whale sound that I recorded from this project that hopefully we'll have time for. I think we will. But yeah. Alrighty. So just in case if anyone does not know, the order Cetacea encompasses modern-day whales. This includes the infraorder Odontoceti, or toothed whales, and also the infraorder Mysticeti, or baleen whales. Baleen whales, or Mysticeti, this group is the focus of my research in the region. So before I dig into my baleen whale specific research, I want to give some background on whales in general, as they're all affected by similar things and they have similar importances. So whales demonstrate their importance in many ways. They occupy a variety of ecological niches, such as with the phenomenon known as the whale pump, where whales cause the mass transfer of nutrients through the ocean just through their large body sizes and their travel across the ocean, both horizontally and vertically throughout the water column. Um, they provide both cultural and economic value to communities worldwide, and they also are part of and interact with oceanic food webs. So whales face a variety of threats, including anthropogenic noise, and really this is all anthropogenic, but anthropogenic noise, incidental and intentional catch, pollution in the ocean, and vehicle traffic. Now, whale research, therefore, is vital to improving our knowledge of these species and addressing the threats that they face. Whale research has its set of challenges, however, as does many things. Traditional whale research techniques, such as boat-based visual surveys, where a boat goes across on these lines. You can see these track lines here from a study by Borden et al. 2022. They cover these lines and they basically just look for whale surfacings. Um, they can be effective, but they can be costly and because of that may only cover small areas, leading to global data gaps. So some more recent research, such as fixed passive acoustic monitoring, where acoustic recorders are fixed to the seafloor, like you see in the middle here, where there's two different acoustic transceivers or recorders fixed to the seafloor here. They can kind of collect a little bit more data, more information about these species, but can still be limited spatially. And we see with whales, obviously, they are migratory, so they have high species mobility, which indicates that it could be useful to have more mobile research platforms to study them as they travel across these areas. So autonomous underwater vehicles like Slocum gliders have emerged in recent decades as an effective research tool that could complement these other techniques and help fill the gaps in our knowledge of these animals. So now I kind of will take us to my project as well as just what we know about these whales in my study region, the United States Virgin Islands and Puerto Rico. So there is some documentation um, for whales in the Caribbean, which includes this particular region I'm studying. We have species, baleen whale species, including the humpback whale, the common minke whale, the sei whale, and the fin whale. So these are the only four baleen whale species we have documentation of in the area. We know they use the Caribbean as a wintering grounds to mate and give birth, coming down around the beginning of the year through May-ish. Um, but the data that we have beyond that of humpback whales in the region is sparse. So we know the most about humpback whales in the area, but the other three species we know less. Um, so, for example, humpback whale aggregations and song have been well documented in the Caribbean, but the minke whale, which has been moderately studied in the area, only really has research documenting some of their calls, but not really their distribution or their site preference, the areas they choose in the region um, for reproduction. Um, and then our sei and fin whales, we know even less. So documentation on these species really just comes from sightings of maybe a handful of individuals, such as like 4 to 5 individuals of the sei whale, or stranding events that have been documented and recorded around the Caribbean of fin whales and sei whales. So that brings us to my thesis research, which is to determine the species of baleen whales and their distribution around the United States Virgin Islands and Puerto Rico using passive acoustic monitoring equipped Slocum gliders in tandem with two different whale detection algorithms. These are the LFDCS, or Low Frequency Detection and Classification System, made by Baumgartner and Mussolini 2011. This is for identifying specifically for this project humpback whales, sei whales, and fin whales. The other algorithm I'm using is called MinkeNet, a fairly recently developed algorithm, particularly for minke whale detection. This is by Moy et al. 2025. The minke whale has slightly different calls. They don't really have song. They have more of what are called pulses. So that's why the other algorithm can't really handle detecting them. So that's why I'm using these two different ones. Okay, my research questions. They are, what baleen whale species are present around the USVI and Puerto Rico? Does time of day or glider depth influence whale detection or the intensity of detection? So essentially, when they are detected, how many detections do we get of their song or their calls? And how precise are the two different algorithms I'm using in automatically identifying the species of recorded whale calls that, with the sound that I run through those algorithms? So, data collection. To answer these questions, I conducted 8 glider missions in the fall and winter of 2024 and spring of 2025. These missions were not only for my own research, but also for the collection of high frequency sound, which are more for animals like sperm whales and dolphins. But we also collected a lot of oceanographic or environmental data during these missions. Um, so you can see here this map of my study region, the U.S. Virgin Islands, which are these 3 islands: St. Thomas, where I'm located, St. John, and St. Croix, and then Puerto Rico to the west. Now we've sent our gliders on a couple different kinds of paths. We have several that are kind of these longer track lines that go cover many different areas only once. And then I can't really zoom in, but you have kind of these smaller shapes around the south shelf of the northernmost Virgin Islands that are kind of doing what we call a time series, where they're covering just the same area in a loop to see how things change in a single area. Alrighty. So this top figure, which is adapted from Mellinger et al. 2007, depicts the known frequency ranges of my 4 target species. So the thick blue horizontal lines represent the most common call frequency ranges known for these species, and if present, the thin black horizontal lines represent the recorded frequency extremes of the associated species. Um, now, I have a little key here on the left, as well as just the vertical lines you see. The vertical black lines indicate the DMON2 frequency response range. The DMON2 is the hydrophone system that I'm using for this research. This is its maximum range from low to high frequency, what it is capable of recording. Um, and you also see the vertical blue lines, which represent the boundaries of the DMON2 low frequency hydrophone recorded frequency range. So this is essentially what I was recording at for just the low frequency hydrophone for my research, which really you can see covers most of the frequency range of my 4 target species here. The humpback whale is, their calls extend sometimes outside of this frequency range that I've set. But you can really capture most of the calls they make. Now, lastly, the vertical pink lines, just if anyone is curious, represents the range of human hearing. So our human hearing really covers most of the sound that they make. Now the bottom image is just kind of a figure of the DMON2 system. On the left here, you can see this kind of urethane housing in the payload bay or the science bay of the Slocum glider. It houses 3 different hydrophones. So there's the low frequency, medium frequency, and high frequency hydrophones. For our research along these 8 missions, we recorded only with the low and high frequency hydrophones. And for my research specifically, I recorded and analyzed the data only through the low frequency hydrophone here. Now, using the low and high frequency hydrophones really cover a majority of the range that we see of the sounds that these animals produce. So we really are pretty covered. We don't need the medium frequency hydrophone. Okay, so summary of the missions. From this effort, these 8 glider missions, we had gliders in the field for a total of 180 days across 2024 and 2025. We traveled a total distance of approximately 3,480 kilometers. Um, the max glider depth slightly varied depending on the mission, the bathymetry as well as our questions. But the average max glider depth was 508 meters. So most of our glider missions, the glider remained around 500 meters, but there was one mission that we were kind of testing the glider. We got it down to about 900 meters. Um, And then the total number of DMON recording days is 128 days. So this is 128 days of recordings out of the 180. This is partially due to the fixed hard drive on the DMON system filling up or completing before we could recover the glider. So it filled up before we actually recovered the glider in the field. And we also had one DMON failure during one of our missions that accounted for a lot of the loss in recording days. So data analysis. I've recovered my data after each of these missions, and I start kind of sifting them through, putting them into the two different detection algorithms. So the LFDCS, again, that I mentioned, and MinkyNet. And so if whales were present, if whales were detected by these algorithms for these missions, I then would run a detection precision score, where essentially the precision score is just a simple equation, the number of manually verified detections, so ones that I went through manually after the algorithm picked up what it thought were whale calls, and I confirmed they were or rejected that they were not whale calls, and I divided that by the total number of algorithm detections. I also, where there was enough data and whales present, um, I kind of investigated the deal cycle or 24-hour preference of whale calling of each detected species using a hurdle model and Rayleigh test. These two tests were chosen really because there was pretty high zero inflation as well as over dispersion. So I picked these two to kind of account for those. And the Rayleigh test, which is similar to the hurdle model, but is a little bit better for accounting for the circularity of time, that midnight is really closest to 1 a.m. So on and so forth, or 2400 hours is really closest to 100 hours. So I did that. And then I also analyzed the effect of glider depth on whale call detections using a hurdle model for the same reasons. Now, if you remember this slide, after running all data sets through these two algorithms, I detected for certain the humpback whale and the minke whale, and possibly sei whales. There were only like 3 or 4 detections that were possible detections, so I couldn't really do any statistical analysis with these, but with the other species I did. So the two missions that for which whales were detected were missions 6 and 7. You can see here this kind of gray small time series to the south of St. John, off the shelf and several thousand meters of water or deep water. And then also this mission 7 here, which is this kind of cyan colored line that goes down to the economic exclusion zone or parallels it of the British Virgin Islands and goes around St. Croix and back. These two missions were conducted back to back in the spring of 2025. And this is kind of, this aligns really with when we expect baleen whales in the region to be arriving here. So I have two figures here of mission 6, which is the one that was just kind of a time series off the shelf. And you can see here on the left is for the humpback whale detections, and on the right is for the common minke whale detections. You can see the gray line is really kind of the overlapping glider track, so it gets a little mixed together with the other glider track lines and makes just this big triangular shape. But just know that the glider looped repeatedly in this triangle shape. And you can see that each of these red dots is essentially the size is based on the number of detections in that area. So interestingly, for both of these detected species, you can see that the detections were highest on the southwestern edge of this triangle and the southeastern edge of this triangle. So really, the further that these species were from the shelf edge, the more detections there were. And this could be explained possibly by these whale species habitat preference, or maybe the way that sound propagates off the shelf slope, or possibly other explanations as well. Now, mission 7 is also interesting, a little bit different than the time series, but you can see that you have these same red circles, the size indicating the number of detections by hour in hour bins. And there are some similarities with both of these species where you kind of see hotspots along shelf edges and even in between these different parts of the shelf, kind of in these big trenches. And not so many detections kind of to the further south of where the glider passed. and also to the south side of St. Croix. There's not really as many detections. Um, there were overall more detections for minke whales, and you still see this kind of gap here in detections. The smallest dot here really just means that there's 0 detections by hour. Um, so just some interesting points there. It is also important to note that these areas where there were no detections made by the glider does not necessarily mean that whales were not there. It could just mean that whales were there but not calling, or they were just outside of the detection range of the Demon hydrophone, um, or they were they could have not been there. But there are some explanations for why they were not detected, but they could still be there. All right. So, a results summary. Significance in the hurdle models and or the Rayleigh tests for each of the humpback whale and minke whales across mission 6 and 7 indicated that there was really a peak in calls, in detected calls around midday. So this was with a range of about 11:15 a.m. to 12:36 p.m. So we really saw across both of these species, they peaked, their calling activity or number of calls peaked around midday for these two different missions. For the depth analysis, only the time series of mission 6 was or indicated that there was a significant positive effect of glider depth on humpback and minke whale detection. This is really only up to the maximum depth of the glider. So it's important to note that we didn't go further than that for the most part, and we didn't go further than that in these two missions. So it's possible that the results would have been different had we sampled deeper. So something to investigate in future research. But for our case, it was found that as the glider depth increases, the likelihood that we would detect humpback whale calls increased. Now, our precision scores for each of these missions and detectors. Um, Across missions 6 and 7, where we looked at humpback whales, the precision scores were 40.6% and 55.4%. And the detector precision for MinkeNet for minke whales across these two missions was 32.4% and 30.8%. Now, there are some explanations for this as well, which are that, I used pretty low confidence intervals just to make sure that I was inclusive of as much data as possible and tried to detect whale calls that may have been excluded if you had a higher confidence interval in these algorithms. But also, these algorithms are trained with previously recorded whale sound. So they're not exactly, presently up to date. So at least what we know with humpback whales, which change their calls yearly, if not more quickly, they are changing their calls. So we could see that this precision score is fairly low because of that. So I'm hoping to, in future research, update the call libraries for these two algorithms and see what we can find, see if we can increase those precision scores. So quickly, the broader impacts. I aim to contribute baseline data regarding baleen whale presence and distribution to the growing pool of research in the region. This study also was one of the first to use the Minke net in the Caribbean. The data that we've collected here can be used to update and improve detection algorithms, like I mentioned, for baleen whales in the region. And I'm also hoping to inform and improve whale conservation, and provide information to developers for safe offshore wind farms so that they're not really, or they're minimizing their interaction with whale species and their corridors that they use. Okay, so we're just about done. I wanted to play two different whale songs that I recorded that I thought were interesting, and then I'll have questions at the end if there's time. So this first one is an interesting humpback whale song that I recorded. You can also hear some extraneous noise, including like a loud pop that might be the platform, the glider noise, or something else. Kind of unsure, but without further ado, here's the humpback song. Hopefully you can hear it.
I don't think we're getting it, Josh.
No, okay. Might just skip it then. Sorry. Well, if anyone is interested, I have an email at the end. If you want to hear whale sounds, then I can show you at the end. But essentially, this is a spectrogram image or a visualization of sound and you can kind of see these kind of sloped white lines are the sound that the whales are making, including these lower frequency ones. Um, and it's just kind of repeatedly making this similar whale call, which is interesting. Um, and then here you won't be able to hear it again, unfortunately. But these kind of tall vertical lines are what are called the minke whale pulses. And so it's just kind of a repetitive pulse. Um, that sounds pretty interesting. So again, if anyone's interested, you can email me and I'll share some sound with you. But with that, thank you. Sorry for the chaos of all the slides and images. But let me know if you have any questions.
Awesome. Great job, Josh. Thank you. Yeah, if anybody has any questions, feel free to either type them in the chat and I can read them aloud, or just unmute yourself and knock yourself out. I got a quick one for you, Josh.
Sure.
The depth dependency you were finding, are you considering taking it into like the temperature salinity space, or like the um looking at any of the other environmental data the glider collects and seeing how that relates to the detections?
Yeah, I think that would be pretty interesting and something to investigate, once I defend and graduate. I want to do it. I'm a little hesitant though because the way that I analyze my data, I had to just for time's sake bin detections by hour, so I don't have exact timestamps of each individual call. So that if I had done that, it would have allowed for kind of a smoother interpretation of whale calls with depth over time, and then I could align better the data we collect about temperature and salinity. So I could still try and see how it looks with the hourly band detections, but um, for our next upcoming research, maybe I'll try to see if I can do individual timestamps of each call so I can get a better comparison to see if there's any relation to environmental data.
Cool. Any other questions? All right. Well, thanks, Josh.
Yeah,
Maybe
thanks,
we'll
guys.
go on over to Leah now. So while you get set up, Leah, I will introduce you. So Leah Hopson is a fourth-year PhD candidate working with Dr. Travis Miles at Rutgers University in physical oceanography. Her research interests focus on the interactions between the atmosphere and the ocean, with a particular emphasis on the complex relationship between tropical storms and the upper ocean. Part of her dissertation work examines ocean column characteristics and response during Hurricane Beryl from 2024. She utilizes observations from an underwater autonomous glider to analyze how the ocean evolved during a major hurricane in the Central Caribbean. Take it away, Leah.
Thank you. Can you see my screen without?
Yep.
Okay, cool. All right. Well, thank you everyone for having me. I'm excited to give this talk. So yes, my name is Leah. I am a fourth-year PhD student at Rutgers University, and my dissertation looks at air-sea interaction. So this fun space of understanding ocean movement underneath these major hurricane events. And so the first part of my dissertation looks at autonomous underwater glider observations during Hurricane Beryl. Okay. So to begin, I want to just give an example of some ocean tech that is being used to help improve hurricane prediction efforts. So to really advance the assessment of upper ocean responses in tropical cyclone model forecasting, it is really crucial to gather and analyze ocean and atmospheric observations from different instruments like drones, sail drones, aircraft, floats, and gliders during these major weather systems. And now to survey the ocean during these events, these really energetic and extreme environments, autonomous approaches are required, right? This work now involves and examines the use and benefits of gliders during an extreme weather event, Hurricane Beryl, which I'll go over later on. So let's tap into some Slocum glider information. I want to briefly discuss the overview of these gliders, but as many of you already know, they offer us rapid sampling of different ocean regions. They also allow us to sample the ocean from the very surface to the depths to very depths of 1,000 meters. And lastly, the data collected from these gliders, like temperature and salinity, have the capacity to be assimilated into forecasting models to better their forecasting efforts and prediction of major hurricanes now and in the future. So with the surveying capacity of these gliders, they can be used in understanding the co-evolution of air and sea. And I, at Rutgers University, we are able to utilize these platforms in different aspects, like during extreme weather events such as Hurricane Beryl. Before I go into some of the glider work that was done, I want to just discuss the storm we were able to sample about. Hurricane Beryl, this lovely storm, was the first hurricane of the 2024 Atlantic hurricane season. And as you see on the right-hand side from the GO-16 infrared satellite image, it made landfall near Matagorda, Texas on July 8th. Now, Hurricane Beryl was a long-lived storm that occurred from June 28th through July 11th, and it underwent multiple rounds of rapid intensification. And lastly, it reached Category 5 status really early on in the season as it tracked through the Caribbean, thus making it the earliest Cat 5 hurricane to be observed in the Atlantic on record. So just seeing and analyzing and understanding all these milestones alone is super fascinating to see, especially when we get the chance to add an ocean observing technology to the mix. So let's look at Slocum glider RU-29, onto the glider that was conveniently used to survey about Beryl. RU-29 was used in a 3-month mission to sample about the Central Caribbean Sea. It was deployed back in April of 2024. We collaborated with folks at Caracas and Puerto Rico, the Caribbean Coastal Ocean Observing System, to help deploy, understand the mission planning and instrumentation, and help retrieve the glider as well. The mission was originally, the glider made a transect of the central part of the Caribbean from Curacao to Dominican Republic, and it was to try to study water mass transport in that region. Also, I want to add that it was a 1,000-meter depth glider, but it did 500-meter profiles when the storm occurred to capture upper ocean dynamics, and we kept it in station keeping position for about 5 or so days during that time. I also want to add that RU-29 was equipped with a few sensors like a CTD sensor, oxygen opto sensor, and our 1 megahertz Nortec acoustic Doppler to current profiler, which is the start of my show. So I want to add that to our knowledge, right, this was the first glider to be able to collect data underneath a Category 5 hurricane. And thanks to Joe, it was piloted very close to the center of the storm, about 17 nautical miles from the center. And although it wasn't towards the eye of the storm, we were in like an intense location. So we were able to capture some really cool data during this storm event. Aside from the work, I want to add that this was an opportune time, a perfect time to do some hurricane mission planning collaboration with different agencies. So at the time that our glider was out there, we collaborated the latter part of the glider mission with those at NOAA AOML and the Global Ocean Monitoring Observing Program. With all the collaboration efforts with the aircraft, sail drone, and glider teams, we were able to communicate with one another to survey about this historical storm and get some fantastic data. And unfortunately, I don't know why it's now boxy, but I guess you guys get the point now. All right, so on to the fun stuff, onto the data that glider RU-29 captured. Now, I want to just dive into some of the data that showed temperature and salinity, but I want to bring your attention to the temperature plot on the left-hand side. As you see, and I added the storm crossing event on July 2nd, a few days before and a few days after, I don't see a lot of thermal change, right? There's less deepening of the mixed layer, which is very interesting to see given that this is a Category 5 storm. I expected more. I expected the energy from the storm to propagate even past 100 meters, but we didn't really see that. Looking at our salinity plots on the right-hand side now, I see a bit of freshwater input, and I'm not quite sure if that's from the Amazon Orinoco River plume or maybe remnants of the storm precipitation. But again, I'm not really seeing before and after a lot of significant mixing. And so that is our question now. What were the ocean conditions or features that reduced significant ocean mixing and sea surface temperature change? And so the use of ocean metrics can come in handy right now. So I will be looking at Richardson number calculations, ocean heat content, and potential energy anomaly. But for today's purposes, I'm just going to look at Richardson number to spare you guys all the nitty-gritty math stuff. So on to our fun 82CP, estimating shear and water column stability. Gliders can be utilized to calculate full and true ocean velocities from our mounted 82CP. RU-29's ADCP was configured to sample in burst mode. I think that's the novelty of the study as well for 4 days during the storm. So we have a bunch of data to deal with. This high resolution data, this robust ocean measurement from the ADCP here and from our CTD, from our density profiles, exhibit the ability to now quantify the relationship between mixing and Richardson number. And I'm going to go into the Richardson number equation just briefly, but essentially Richardson number, or RI for intents and purposes, are often used to describe stability in a stratified fluid. Essentially, it's the ratio between buoyancy frequency, so n squared, and shear over time. And I want to add that RI includes a 0.25 threshold for determining turbulence and stability. So if I have values more than 0.25, I am in this laminar fluid flow, this stable flow. And if I'm less than 0.25, I'm in a turbulent regime, right? So let's go into some of the data that that the ACP collected to help me understand Richardson numbers. On the left-hand side, this is showing some of the horizontal velocities prior to storm passage and after storm passage. But for today, I'm only showing the upcast data for now, and this is showing the upcast east and west velocities and north-south velocities. Now on the right-hand side, I want to focus your attention on this, is showing shear and buoyancy frequency alongside Richardson number calculations. So as we walk through the top right-hand portion of the screen before the storm, we see that from the surface to about 60 or so meters, shear is overcoming buoyancy frequency, and you can kind of see that corresponding to these lower Richardson number values. So we're in turbulent environments, but this is essentially within the mixed layer, so it kind of makes sense. After that, we are tapping into a bit more buoyancy frequency values are higher than shear. And so now we're leading into this stable threshold. And so Richardson numbers are higher. And that shifts again after about 80 meters. And we're toggling the lines of stability and instability. But this is interesting because now this corresponds to some current velocity directional changes. But I'm not sure if that is directly influenced by the storm's energy, or is it from some internal oscillations or wave dynamics occurring around or after the mixed layer? But the fun part is understanding after the storm, and also during, I didn't show during today, but after the storm, it shows that about 40 meters after or deeper, there's a bunch of cases of stable environments. And so this is maybe a hint at this is possibly why there was suppressed mixing during or after storm passage. But of course, I can't just stop there. I must do a robust analysis of both upcast and downcast data to really examine and hone in on shear changes over time and buoyancy frequency changes over time. But I want to combine this effort and information with other ocean metrics and hurricane metrics. So for instance, potential energy anomaly, PEA, that tells me how much mixing or how much energy does it take to fully mix and homogenize this column of water, and also mixed layer depth changes. So these metrics can help me to examine ocean column stability pre and post storm passage, but also address the nuances of air-sea interactions and why mixing was suppressed, given that this was a strong wind forcing case. And now I just gave you so much information right now in a short time, but with that, I'll take any questions.
Thanks, Leah. Awesome as always. Anybody have any questions for Leah? You can just unmute or type them in the chat, whatever's easiest for you guys. I am a co-author on this, so I'm not gonna grill you with questions, but If you were to do it again, would you dive the glider to a different depth now that you're analyzing?
I mean, I guess it depends on what store I'm looking at, right? So if it's another Cat 5, I would probably just keep it at 500. But if it's like maybe a Cat 3, I would maybe show a bit more. But it depends on how fast the storm is moving and what kind of energy will be imparted onto the surface.
Yeah, Adam, go ahead.
Hey, with your glider set up like that, are you able to track or detect internal waves? I can imagine there might be some around that boundary.
Maybe, yeah, yeah. So I think in one of the plots I had, let's see if I can go backwards. Um, Oops, let's go here. Maybe if I look at some of the upcast data and downcast data, I can probably pinpoint some internal wave action, but that's like another part of like examining and what kind of methods I'll be able to do to actually get the internal wave action or oscillations. But that was a good question, and that's what we kind of saw before in some of these plots.
Thanks. It was a nice talk.
Thank you.
Any other questions for Leah? All right. Thank you, Leah.
Of course, thank you guys.
We will move on to Sakib now. So Sakib Mahmud is and while I give your intro, Sakib, you can share your thing. Yeah. He's a physical oceanographer at Texas A&M, the University of Geochemical Environmental Research Group, or GERG, where he leads the autonomous glider operations. His research focuses on estimating ocean currents and turbulence using machine learning and glider observations in the Gulf of Mexico. His background integrates field-based ocean observing, data-driven analysis, and the study of loop current and eddy mixing processes. So I'll hand it off to you, Sakib. We are seeing your presenter mode, just so you know. So maybe switch it around.
Okay. That always gives me a trouble, Joe. Like, I'm not very techy.
But you're flying robots into the loop current, man. You're very techy.
Is it good now?
It's great. Thanks.
The screen good now? Is it showing the correct view?
All good now. Yeah. Thanks.
All right. Hello, everybody. I'm Sakib Mahmud. As Joe already said, I'm a postdoc and I'm running the glider operation for the Geochemical and Environmental Research Group. Today, we're going to talk about estimating the horizontal current with glider observation using machine learning technique and some insight from the program that we're part of called the UGO's Master. The UGO stands for Understanding Gulf Ocean System, and Master stands for Mini Adaptive Sampling Test Run. So we're going to talk about the program a little later, but what we're trying to solve in here. So there is a very lack of measurement of current at depth in the, as we people who are in the ocean operations know, the satellite lack estimating the subsurface current in situ profile like buoys. They are very sparse and location specific. There are gliders that has a ADCP, but also if you compare the number of glider has ADCP in relation to the number of glider we deploy every year, which is very small. So the idea was if we can use a data-driven machine learning technique with a glider with an ADCP and develop a technique that can use the glider standard parameters like hydrography and the what's called vehicle dive parameters to estimate the currents. Why it's matter? Understanding the ocean current is very important. Same with the EGOS program that we're working is specifically designed to understand the loop current in the Gulf of Mexico. If you look in right here, this is the current that you're seeing is the loop current, one of the dominant feature in the Gulf of Mexico, which is essentially part of the western boundary current. And the program is designed to understanding that current. So better current, this means we can expect the better decision making in kind of response of oil spill, hurricane, transportation all this way, and also why looking at the gliders, because as I said earlier today, the glider is much more versatile, is not contained in one location, it's moving and it's collecting data for a longer time. And also thinking that if we can do a machine learning model we can train that can estimate the current that fills the data gap between the actual measurement, which is a cost-effective way to filling those gaps. The project overview, Understanding Gulf Ocean System, is funded by the National Academy of Science, and this is a giant mess right there, what everything going on. But this is essentially a group of ocean observers, stakeholder from state, university, federal agency, different countries, including Mexico, and also the ocean modelers. They all combined with under the project. The idea is improving the forecasting capability of loop current and loop current separation and transit to a established program that can run independently to give a better forecast. So when the data that I'm going to use, we were there, that right, we are here in master. And then right now we pass that phase, we are in the grace, which is the green on the right. But we're going to talk about the data that we collected during the master. Giving an idea how big is the program is more than 60 researchers working under this program from 16 institutes and 3 countries, which is US, Mexico, and we do the observation in Cuban water as well. We did, and currently we're doing as well. So the master field campaign elements was multiple instrument. The idea was adaptive sampling, and we deployed multiple resources, including gliders, 4 gliders, one from Texas A&M, one from Rutgers, and 2 from CSS, which is a partner from Mexico. We also deployed multiple floats, including Apex float, and also background Argo floats, drifters, surface drifters. Additionally, we had the HF radar in, I believe it's called the Islamahaya. I am not sure with the spell like pronunciation, but that is right there and collecting the surface current. Also, the part of the program is a defined oceanographic model where the data is getting assimilated in a real time to update the forecasting. So this is a quick overview that the glider deployment, since we're talking with the gliders, multiple gliders are deployed, and you can see the CSS2 gliders, Rutgers gliders, and TAMO gliders. TAMO gliders during the deployment did not have any ADCP, but all the other 3 gliders had the ADCP that collected the ocean current and the hydrographic profile. On the left in the top, you can see the tracks covered by the different gliders, including most interesting, I would say, of course, entire mission, but that transit from Mexico to Cuba. The Rutgers glider RU-38 and Stommel both made that transit straight. So that's a very good, very interesting data set that we have. So this is left is the area that we saw, and then putting all the asset together, you can see a multiple asset in the left. Those are the gliders. And then we do the ROCAS, which is a high resolution velocity measurement, which is essentially a LiDAR from the plane that fly over and measure the current in very fast time. So there is a video that's going to show different asset over the time, and I'm going to play it. We love this video, and Steve DeMarco, my boss, like shows it everywhere. So it comes with a little sound. So there's a 2 glider going from the CSS. They are deployed from Mahahual, and they're going through this way, and you can see the overplot of the HF radar. And then comes other 2 gliders, Rutgers gliders and TAMO gliders. They're going through, and there at the same time you can see the drifter going flowing. This is the far horizon drifter, surface drifter. And you can see the red line coming in and going. Those are the Rutgers flight. There's a very short time, but very long coverage. And so all this asset put together to get to the point that when we call the master campaign, and all the data get to the models to improve the forecasting. All right. Yes. So talk about the data for the machine learning. The data that I am using in here today from that project is the collected by the RU-38. The glider has an ADCP. Oh, the RU-38 is operated by the RU-Cool Rutgers. They have the best name in the world. Okay, so the glider has an 82 CP that collected the hydrography and also the current profile. Of course, everyone in this webinar, I assume that everyone knows glider. I'm not going to lecture you about the glider, but in the left of how the typical glider profile look like, those are some flight parameters. And on the right, this panel showing the glider velocity profile that comes from the ADCP. The file that I'm using for this is processed following the guy named Joe Gradone. His standard operating procedure. So this is the ADCP measurement, and the bin size of the ADCP data is 10 meters. However, the glider collect data in a very high resolution is like order of 0.2. So then we have to go to the machine learning model, and we have to do think about multiple way how we do it. So we use an LSTM model and separate the data in the 10-meter bin size. So it's every chunk is a 10-meter bin, and that has all the glider data in that 10-meter bin. This means if the ADCP giving us data for 5 meters bin, then the glider or the model using the bin of data from 1 meter to 10 meter and every data, and then that is using the LSTM model to predict that velocity point from this way. So it's a kind of a chunk of every 10 meters. The model that I'm using, this is LSTM, is this what's called RNN model, and it's a bidirectional 6-layer. And then after that, this is still a black box, which is I'm learning every day. And I'll talk about it later, probably when I know even more. So there are some of the results. On the left top two plot is showing the validation set, the correlation between the true and the x-axis is the ADCP measurement, and the y-axis is the prediction from the model. And you can see the R-square value is up to 91% for U and V. On the bottom panel, this is the holdout set, and that set represent that the transact that I showed you, like from Mexico to Cuba. So since this is a very interesting part, I just hold it out separately to do a prediction. So we said that two and same, the prediction and the measurement from ADCP is more than 91% for U and V. On the right side, if you'll see that on the top is the histogram of the current, left is the U, which is the U velocity, marked as a U true, which is the ADCP, and U predict. And you can see that they align very well. On the right is the V, is the same as well, very well prediction. There's a little bit bias that we're going to talk a little bit, and you can see in the scatter plot as well. The bottom is the residual, so we're missing a little bit of data, but that is, I think, pretty much very good. So on the left side is the Hopmolar plot of the velocities. On the top is the U. This is from the ADCP, and this is U, and this is V on the right from the ADCP. The bottom panel is showing the estimation using the model. So this is U and V, and you can see that there is some pretty good matching, but there's more disagreement. Of course, one thing I wanted to mention there, this is a model and that's not totally designed for high resolution science. That's more of an operational, and we can probably see in a big scale stuff, but not high resolution stuff. On the right side of the panel, I plot a few of the profile as a one-to-one comparison, but you can see that the prediction and the um, ADCP measurement, they're pretty well aligned if you think about the whole line from surface to the bottom, but there's a lot of differences, like uh, model still a little bit more smooth. The few of the difficulties that I have when I was working, I believe that all the differences attribute to the data, because the data was highly skewed to the positive velocities that was deployed in a region where the U and V actually very positive, so eastward and northward. So data was skewed, so model acting differently. The Also, it is definitely not too long to train a big model. So that's all. But the overall picture and statistically, it gives us the confidence that is an acceptable limit that we can report, and we're gonna advance to the next level. So coming to the conclusion, the performance model performed really well. I would say better than expected. And as a full disclosure, this is my first time I'm doing any machine learning model, so it's a kind of trial and run error for me. We get the R square value more than 91%, so the model explained 91%, more than 91% of the variance of the direct observation. The model also captured the general structure of the current throughout that entire section. In operation value, the that can be used in an alternate of the ADCP, especially when there's a glider deployment, but that doesn't have an ADCP. And as an operator, we all know that we deploy way more glider without ADCP in every year. So in middle of that time, that can be used. Of course, it definitely need more study to confirm that, but can be used or has the potential to advance to the level that can be used to predict the horizontal velocities. Next step, the way I'm thinking that we're going to use multiple models to get an uncertainty estimation that what is different model reporting, as well as I am planning to entrain a physics informed machine learning model, which might gives us more advanced and better result. With that, thank you. I will show you the one of a kind picture, sea urchin and sinking a glider. Thank you.
Sakib, super cool. Did you flood a USB glider there? Is that what that is?
Yeah,
Oh man,
it's in the guard tank, the
that's
coral
fun.
reef that we have.
Anybody have any questions for Sakib? I
Rick,
definitely do.
yes, just adding, if you don't have a question, but later have a question, ideas you want to contribute, work together, I'm totally open for it. Shoot me an email, please. Joe.
Yeah, and you could probably throw your email in the chat just in case folks want to need that. But so sorry if I missed it, but what was the input data for the model again?
Temperature, conductivity, pitch, roll, heading, what's called the depth average velocity, fin, just everything that comes out from the glider. So there is no derived variable yet. So when it's gonna be physics informed, that will start introducing different physics parameter, like could be density, buoyancy frequency, which has a huge impact on the glider movement. So
Yeah, so like the underlying model is it's probably just taking the depth average current, but then the shear that you're getting out of it is probably from the
glider attitude sensors and stuff.
yeah, or even the I mean, geostrophically balanced shear from the CTD then would be the only other aspect that could add that physically.
Yeah, we definitely need to talk, Joe.
Yeah, that's really cool. Now I understand what you're doing. So, very cool.
All right, thank you.
Excited to see it. Any other questions for Sakib?
All right, thank you. I'll set my email.
Cool. All right. And last but certainly not least, we have Caroline Wiernicki. Did I say your last name right, Caroline? Cool. So Caroline is a PhD candidate at the University of Delaware working with Matt Oliver and Aaron Carlisle. Her project involves testing and deploying a new type of CTD tag on pelagic sharks in the Mid-Atlantic Bight, with the ultimate goal of shark-collected CTD profiles contributing to hurricane intensity prediction modeling. Her background is a blend of shark ecology, animal movement, and applied ocean observing and robotics. So take it away, Caroline.
Thank you, Joe, and thank everybody for sticking around. Can you guys hear me okay? And do the slides look good?
All good.
Excellent, cool. Okay, like Joe had said, my project is about the testing, validation, and hopefully eventual longer-term deployment of a novel animal tag on sharks in the Mid-Atlantic Bight. And in this presentation, I want to talk to you guys about some of our results for chapter 2 of my dissertation, which was about trying to validate these tags on slocum gliders acting as sort of a control animal for a couple of deployments. So let's get into it. There we go. Cool. Okay, so I'm sure that a lot of folks in this group are very familiar with the sort of physical oceanography structure and kind of concurrent question for making hurricane predictions in the Mid-Atlantic Bight. The Mid-Atlantic Bight is characterized by a very strong pattern of seasonal stratification with the presence of the cold pool and that upper layer of water heating up over the summer into the start of hurricane season. And while federal agency and research institutions have improved with predicting arrival times for storms over the past several decades, the ability to correctly predict intensity, now we're on timers, that's okay, has lagged a little bit. And this is tied towards mapping the upper ocean heat content in this area related to this stratification. So more stratification, a little bit harder to predict intensity. And one strong example we saw with this was the comparison between Tropical Storm Irene in 2011 versus Hurricane Sandy in 2012, where there was a mismatch between predicted intensity and intensity upon arrival related to the availability of temperature data and the location of the cold pool. So we need more temperature data. And current methods, mainly including the glider fleet, have been a very successful tool in the toolbox. They do remain a little bit spatiotemporally limited. Gliders tend to be a bit slower, 20 centimeters per second, with the deployment windows of 4 to 6 weeks. And so one question that we have is, can a new type of quote unquote autonomous platform, semi-autonomous, the animals will do what they want, help us fill this data need in the Mid-Atlantic? And so this is tied towards a broader interest between animal telemetry and oceanographic observing groups seeking to use marine animals as ocean observing platforms. And so one example, this technology really kicked off with the deployment of a novel CTD tag on air-breathing elephant seals in Antarctica in the early 2000s. Antarctica in the winter is not a place that many people like to sample. And so the deployment of these tags over one winter season actually increased the amount of data available. That is getting very annoying, I apologize, by 3,000%, the number of profiles from these tagged animals. So there really is untapped potential with using these animals to sample habitats in situ that might be less easy to get to with boats or drones. So here we have a map of marine mammals deployed with these CTD tags over the course of this broader MEOP project that started in 2003. You can see this little box for our mid-Atlantic area does not have many tracks in it. We don't really have a ton of marine mammals in the same density, but we do have a number of sharks. And so there are over 19 species of sharks in the mid-Atlantic bight. Many of them we know surface and dive regularly. And over the past few years, there's been a push in interest with this Animals as Ocean Observing Groups to explore water-breathing animals as possible platforms to carry these tags, with successful deployments on a tiger shark in Hawaii over the past couple of years, as well as on a salmon shark in Alaska. And so this question for this talk is, okay, we're thinking about using sharks versus gliders to collect operational oceanographic data with an end goal of using and assimilating into hurricane models. And that begs the question of, this sounds great on paper, but how well will these tags actually perform in the wild? So what is a baseline sensor performance? You know, we're thinking about glider motion versus animal motion. There's a lot more variability. And for our region, the Mid-Atlantic bight, we're interested in capturing stratification, which with possibly a more variable sensor and a more variable platform might have some implications for the quality and usability, utility of our data. So we need a control, and this is where the gliders come in. So the objectives of this talk in this project were to characterize a baseline of shark CTD tag sensor performance compared to the established glider CTD platform by deploying tags on gliders for a couple of missions. And then with this data to also look at possible environmental impacts on tag performance, so mainly that stratification question, and then to see if we can quantify the impacts of platform motion on our tag performance, so speed and angle of attack. So to get at this question, we deployed a CTD tag on a G2 and a G3 in 2022. You can see the maps of the two paths on the side of the screen. The black is the G2, the gray is the G3. And so we had one out in March for 25 days in homogeneous conditions, and then one out in September for 26 days in more stratified conditions. And just to give a little more context to the sensors at hand, so we have accuracy and resolution in lab tested settings for our tag and for our gliders. The main things I want to point out is that the CTD on our tag, you see that little box on the side with the numbers on it, that's a non-pumped CTD port that samples at 1 Hertz. So we're comparing that to a 0.5 Hertz continuously pumped CTD on our glider CTD. Conductivity is not as great accuracy and resolution. Temperature is more comparable. And our pressure is operating at a similar resolution over a much higher depth range, which we'll see the effects of that as we go through the rest of the talk. And so looking at the data we collected from both of these missions, here's just the temperature profiles collected by our gliders in March and September, mixed and stratified respectively. I just want to point out that we really do have a nice thermocline setup in that stratified mission. And if you look towards the end of the mission past October 3rd, that was actually when the remnants of Hurricane Ian rolled by, Tropical Storm Ian. And so for the rest of the metrics and stats I'm going to talk to you guys through, we're discarding those those 7 days, that last week in the mission, to really compare mixed versus stratified. So we had our tag and our glider out in the wild, sampling concurrently during these 2 time windows and these 2 sort of temperature regimes. So our first question was this baseline assessment of tag sensor performance. We wanted to look at this by looking at just root mean square error and bias between temperature, conductivity, and pressure. We've got a sample yo on the figure on the right. The full yo is that first column. Blue is glider, orange is tag. And if we zoom in on the trough of those yos, we can see that there's a little bit of a mismatch off the bat. This is the raw data taken off both devices. And we do have both a lag in the clock and the tag, which was mounted 8 centimeters above the glider CTD, in fact, believes that it is 2 meters below. So possible little bit of a snafu there. So to address the clock lag, we just calculated a cross correlation function on that bottom 2 meters of each yo with those two subsets of data for each yo approximated to a 1 second interval to get a lag between the two devices. And so the histogram shows you the distribution of lags calculated for every yo in our mixed and stratified missions. We have quite the range. As you know, when the glider comes to the surface to get a fresh GPS, it resets the clock. For our shark tag, we don't have that luxury. So over the course of deployment, we would expect to see a clock lag accrue. These tags have the potential to go out for up to a year. So having some type of metric to estimate and back apply a correction will be nice. So if we do a useful but not super strong linear regression, our R-squared for our mixed mission is 0.14, and for our stratified mission is 0.5, which is much better. We can start to approximate what a correction like that might look like. So for our mixed mission, a 1 second correction to the O's every 21-ish days, and for our stratified mission, every 5-ish days. And again, we're interested in seeing how this tag would operate in a stratified conditions. So I'm going to move forward by focusing on those stratified mission results. So I had mentioned for this baseline assessment, we were interested in looking at root mean square error and bias. For the sake of time, I'm just going to show you root mean square and error results for the glider and tag temperature measurements and glider and tag pressure measurements. The lighter colored boxes are calculations if we did not apply that clock lag correction. The darker colored boxes are with that correction. And so this is basically showing that that 1 second lag over 5-ish days or so has an impact on our error. We're looking at as well as, looking at crests, downcast troughs, breaking up our yos based on the movement phase. We do see differential responses to how well that tag's not unpumped CTD is performing. And if we just keep moving, this is just a table showing those overall summary statistics for each measurement sensor. The main takeaway is that during our stratified mission, we do see significantly higher errors across the board. The tag measured deeper pressures and higher conductivities. And then with our mixed mission measured cooler, and our stratified mission measured warmer. So moving into our second objective, we were also interested in seeing how stratification, again, that pre-hurricane season warming period might impact the tag performance. So we calculated stability, buoyancy frequencies, which I mentioned earlier today, and then looked at that temperature root mean square error for our profiles as a function of both N2, the intensity of N2, and then the distance from the depth of a max smoothed N2 as an estimate of a picnic line. And this is showing for just that comparison with N2 that we do see the strongest effect on temperature root mean square error for the tag with our stratified upcasts. And again, this is the time of year we're interested in sampling. And can we try to use some of these coefficients to estimate and potentially back calculate some kind of correction in the field when these tags go out on sharks and when we're just getting that tag data back. And then when looking at distance from that estimated maximum picnic line, top row is that mixed mission. When stratification was detected, and I didn't apply a threshold for these figures, it was very weak errors and very weak stratification values. And again, with our downcast and more so with our downcast and with our upcasts, we saw the maximum error occurring 26 decibars below our downcast depth, and then below picnic line depth for our downcast, and 16 decibars below picnic line depth for our upcasts. So we're seeing a temperature lag and a clock lag at play here. And so I realize I'm close on time and moving a little quickly here, but our last objective was to start to try to tease at platform motion. And so we ran a dynamic flight model from the glider flight packet in Python on both glider missions. Given that we were in a shallower environment on the continental shelf, we masked inflection depths less than 5 meters and greater than 100 meters to find our coefficients based on ballasting coefficients. and then a zero lift drag coefficient based on previous studies, estimated coefficients with a micro rider, which arguably is a larger profile than just our tag. So happy to talk to folks if they've got ideas on how to fine tune that a bit better. But this was just an interest in looking at temperature, conductivity, and pressure as a function of these flight parameters. And I want to give a shout out to Joe for working with me to start parsing through these flight model equations and code. And so this is just an example of sort of what those, the flight model is basically balancing lift and drag forces for the glider, estimated based on its actual path parameters and pitch angles. And it allows you to estimate angle of attack, horizontal glider velocity, vertical glider velocity, and incident velocity. And so our question was, given that we have this controlled platform, we can watch and measure and see how it's flying, how that might impact to sort of brace as a control for an animal operating in space that we can't control and is operating at a higher variability. And so this is just looking at average glider horizontal velocity. And we didn't really see a ton of a response here, looking at the difference in temperature between the glider and the tag as a function of velocity. And if we sort of expand, I'm sorry, this plot is a sin given how complicated it is for a talk, but I just want to sort of show that we see this kind of shotgun blast effect for our horizontal, vertical incident velocities and our attack angle. And while this wasn't quite, what we were expecting to see, it's not necessarily a bad result as far as the null result goes, and perhaps suggests that maybe this lower limit of lower speeds and more regular fluctuations in movement, we don't need to worry about that as a source of error for our deployments on animals. Though there might also be a binning and a resolution question here. So this is still being tweaked and looked at. And so in conclusion, our CTD tag in its current form, that clock lag over time is a bit of a concern. And so looking to continue to refine and try to back calculate corrections for that lag that we can apply depending on, mixed versus stratified conditions, time of deployment. Our upcasts had higher root mean square errors in stratified conditions across the board. And this has an exclamation point behind it because the next iteration of the tag intended for longer term deployment for a duty cycling concern only sends back those upcasts. So, is it worth looking at the programming again to, find a sampling interval that lowers that root mean square error, or can we sort of work with the sensors and with the engineers designing these things to control what we can, or just, again, try to come up with coefficients based on these controls we have to apply for when we don't necessarily have that information when the tag is out on a shark. Not a huge surprise, but, stratification had impacts on accuracy and error. And it's something that, again, we hope we can track to a certain degree. And that this potential lack of a relationship with the glider movement, it's a negative result, but it's not a bad one, as again, it's one more thing potentially that we can estimate out. And so with that, big thanks to the members of the Orb Lab and the Carlisle Labs at UD. This is a project that's been funded by NOP and working closely with Maricus with the ultimate goal of linking these shark collected profiles into the GTS. And then shout out to the folks at the Sea Mammal Research Unit at St. Andrews who have built the tag and been working with us, and the fine folks at Teledyne Marine Glider Support, as always. So with that, I apologize, I'm talking like a fire hose, but happy to take any questions.
Super cool, Caroline. Thanks for sharing. Anybody have any questions for Caroline? I've got a quick one. The clock lag, is that I might have missed this because I had to mute or like jump out of my office for a quick second, but is it a lag or is it like a drift over time?
So
I guess they're kind of the same thing, but is it,
what do you mean by drift? I guess you could call it it is more of a drift because we do see, you know, like the variability that lag happens over each mission. Like the distance of these points stays relatively consistent over time, but it is making its way into broader ranges or ranges between higher numbers. So I guess it's perhaps is a little bit of both.
Is it something that, so you're working with like the tag manufacturer? Is it something that like you're feeding back to them and that hopefully it's not like they're doing different iterations of the technology, you might improve that?
Yeah, I think one possible, I am not an engineer. It would be great, you know, like if there was a way when the tag comes to the surface, it's seeking out a GPS fast lock. And so I'm not sure how much more of a program load or a battery load would be to try to just sync the clock in the moment. I know we have some issues with our gliders being able to get that GPS and clock sync when they're at the surface for a little bit longer time. But seeing how just the lagged and versus unlagged data can impact the spread of errors and points received, I think it's something that's worth looking into for these tags going out there in the long term to collect usable data.
Yeah, super cool. Any other questions for Caroline? Going once, going twice. All right.
If I can chime in real quick, sorry to interrupt. I know that there's a lot of folks in this room who do a lot of work with, you know, data collection for operational use. And one question that we have is, okay, we've now quantified how the tag performs to a glider and sort of what its limitations are and pros are in different spaces. And so what does this mean as far as possible utility and assimilation in these hurricane models or in practical space? You know, I've been digging through the Portad manuals and looking up IUSE key variable criteria, and it's kind of like, well, what is good enough, or what is perhaps not good enough? And so that's just a broader question that I've been pinging around and looking for that, you know, actual applied answer to. And so if anyone has ideas or wants to chat, I'll put my email in the chat and would be really, really keen to pick your brain.
Caroline, I'll say we feel like very general statement. Cortad's a good start.
Yeah.
That's the feeling. That's a start. It's definitely not the end game, but it's a start. Same with HF radar, but yeah.
I'm sure Scott would have a ton of thoughts on this, on data quality going to the operational models. So either I can connect you with him or Matt for sure. But he's definitely got his finger on the pulse of that world pretty well. So
That'd be awesome.
yeah.
I'll follow up. Thank you. Thank you, Bob.
Cool, guys. Well, I think that's it on my end. My Vanna White time is done, but I want to thank everybody. Super cool presentations as always. Don't forget to put this in as an invited talk in your CV. And I think I'm kicking it over to Cassie.
Thanks, Joe. Yeah, thank you to our awesome speakers. Those are really great presentations. And thank you, Joe, for helping to facilitate. Just to close this out, a couple quick reminders. We do this webinar every 2 months. So if you have any ideas for webinar topics, things you'd like to present on, be on panels for, or just hear about, feel free to send an email to info@underwatergliders.org or Georgia Coward. And that email is also on our website as well. And then if you'd like to join UG2, if you're not already a member, or just get involved in our Slack channel, you can sign up on our website as well. So I think that's it for us today. Thank you all for joining, and I hope you enjoy the rest of your day.
All right. Thank you all.
Thanks, guys.
Thank
Thank
you.
you.
Thank you.
Thanks, Cassie.